Imagine you're looking through a telescope at a single faint star waiting. You know that in a few seconds, a small frozen world far beyond Neptune is going to drift in front of it, and you know exactly what that should look like. The star should snap off instantly like a switch because the world doing the blocking is a bare dead rock, and bare dead rocks have sharp edges. So you watch and you wait, and the moment comes. But the star does not snap off. It fades, slowly, softly, over a second and a half, as though something invisible were wrapped around that little world, bending its light. There is only one thing in nature that does that, and it should not be there. What would it take for the deadest world we know to grow a sky? Get cozy, subscribe if you haven't already, and stick around, because that single fading star has forced scientists to reconsider everything they assumed about the thousands of frozen worlds at the edge of the solar system. Let's dive in. Part 1. The Edge of the Map. Picture yourself leaving Earth behind. Not in a rush, not in a roaring launch, but slowly, the way you drift towards sleep, letting the planet shrink beneath you until the blue and white of it is just a marble, then a dot, then nothing you can pick out at all. You pass the moon. You pass the orbit of Mars, that small rust-coloured world that so many people dream of reaching. You keep going. Jupiter swings by, enormous and banded, with its great storm and its little family of moons. Saturn follows, wearing its rings like a thought someone had and never finished. And still you keep moving outward, past Uranus tipped over on its side, past Neptune glowing a faint and lonely blue, until the planets are all behind you, and there is almost nothing ahead but the dark. Out here, something has changed about the sun. For your whole life, the sun has been the most powerful thing in the sky. A disk you cannot look at directly, a source of warmth you can feel on your skin from 93 million miles away. But from this distance, the sun is no longer a disk at all. It is a point, a brilliant point, brighter than any other star, but a point all the same, throwing almost no warmth, casting a thin and silvery light that barely reaches the things drifting around you. If you held up your hand, you would see your own shadow, sharp and faint, but you would not feel the sun on your palm. Out here, the sun has become just another star, the brightest one in a very cold sky. This is the region we're going to spend the next couple of hours inside. It has a name. We call it the Kuiper Belt, and it begins past the orbit of Neptune, roughly 30 times farther from the sun than the Earth is, and it stretches outward from there into the dark. It is a ring, or really a thick disk, of frozen leftovers. When the solar system formed, 4.5 billion years ago, it formed out of a spinning cloud of gas and dust, and most of that material gathered together into the sun and the planets. But not all of it. Out here, where the sun's pull is weak and the cold is absolute, a huge amount of material never got swept up into a planet. It stayed scattered, in pieces, in countless icy bodies ranging from specks of frost to worlds hundreds of miles across. The Kuiper Belt is what was left over. It is the construction site of the solar system, never cleaned up, frozen in place exactly as it was when the planets were young. For a long time, scientists thought of this region as a kind of frozen graveyard. I want you to hold on to that phrase, because we're going to come back to it more than once tonight, and by the end it is going to mean something very different than it does right now. A frozen graveyard. A place where dead things lie undisturbed. The idea was that the objects out here, these distant chunks of ice and rock, were the most boring objects in the entire solar system. They were thought to be simple, small, frozen solid all the way through. No heat inside them, no weather, no geology, no change of any kind. Just silent relics, drifting in slow enormous circles, preserving a snapshot of how things were billions of years ago, and otherwise doing absolutely nothing. If you wanted excitement in planetary science, you looked at volcanoes on Io, or storms on Jupiter, or the possibility of an ocean under the ice of Europa. You did not look out here. Out here, the textbook said, nothing happens, and nothing has happened for a very long time. I want to be fair to that old picture because it was not foolish. It was built on solid reasoning. These objects are unbelievably cold, only a few tens of degrees above the coldest temperature that is physically possible, the temperature we call absolute zero. At those temperatures, Most things that we think of as gases or liquids are frozen into hard ice. Water out here is not a liquid you could drink or even a slush you could push your hand through. Water out here is a mineral, as hard as granite, as rigid as the rock under a mountain. And these objects are small, most of them far too small to hold heat for billions of years or to keep any kind of atmosphere wrapped around themselves. So the reasoning went like this. They are too cold to do anything. They are too small to hold on to anything. Therefore they are dead. Therefore they are boring. Therefore we do not need to look very hard. Let me give you a feeling for the distances involved, because they are so large that the numbers almost stop meaning anything, and I would rather you feel them than just hear them. The Earth orbits the Sun at a distance we call 1 astronomical unit, about 93 million miles. That is already a distance the human mind cannot really hold. Light, the fastest thing there is, takes about 8 minutes to cross it. Now the Kuiper belt begins around 30 astronomical units from the Sun and stretches outward from there, 30 times the distance from the Earth to the Sun. Out where our little world drifts, sunlight that left the Sun does not arrive in 8 minutes. It takes hours. And the Sun's warmth, spread thinner and thinner the farther it travels, arrives so weakened that it can barely be said to arrive at all. There is a useful way to picture how the strength of sunlight fades with distance, and it is worth holding on to because it explains so much about why these worlds are the way they are. The light from the Sun spreads out as it travels, like the surface of an expanding balloon, and the farther you go, the more thinly that same light is stretched across a larger and larger sphere. The effect is dramatic. By the time you reach the Kuiper belt, the Sun delivers something like 1,000th of the light, and heat it pours onto the Earth, and in some reckonings far less than that. Imagine standing in full noon sunshine, and then imagine that same sun dimmed 1,000 times over, and you begin to understand the kind of perpetual deep twilight these objects exist in, a twilight that has never once brightened into day in 4.5 billion years. And the cold that comes with that dimness is not the cold of a winter morning, or even the cold of the polar ice. It is a cold so extreme that the very idea of a substance changes. Gases you breathe every day, if you carried them out here, would not stay gases. They would freeze into solid ice and fall to the ground like snow. The chemistry of warm worlds simply does not apply. Out here, in this perpetual twilight, the rules of what is solid and what is liquid and what is gas are rewritten by the cold, and almost everything that moves and flows on Earth lies frozen and still. And that, it turns out, was the mistake. Not a mistake in the math, not a mistake in the physics, but a mistake in a much quieter and more human sense. It was the mistake of deciding that something was finished before we had really looked at it. Because in the last couple of years, astronomers pointed their instruments at one small, anonymous, supposedly dead object in this frozen graveyard, and what they found broke one of the rules we were most confident about. They found something that, according to everything we thought we knew, simply should not be there. And the strange thing, the thing that keeps the people who study this awake at night, is not just that it is there, it is that we cannot yet explain how. So get comfortable, because we are going to travel all the way out to the edge of the map, to a world you have almost certainly never heard of, and we are going to find out why a single faint flicker of starlight has quietly forced scientists to rewrite a chapter of planetary science. And we are going to start with the most ordinary object imaginable. Part 2. The most boring object in science. The object at the centre of this story does not have a romantic name. It does not have a name at all, really. Not the kind of name we give to things we love or fear. It has a designation, a string of numbers and letters issued by the people whose job it is to keep track of the millions of objects orbiting the Sun. The designation is 2002-1593, and more recently it was given a catalogue number as well, 612533. That is it. That is the whole of its name. 2002-1593. The 2002 at the front tells you the year it was discovered, because it was first spotted in December of 2002 by a survey at the Palomar Observatory in California, one of countless faint dots that survey telescopes pick up as they sweep the sky looking for anything that moves against the background of stars. When it was found, it was just another entry in a growing catalogue. By the early 2000s, astronomers had realised that the Kuiper belt was not empty, that it was in fact full of these objects, and they were finding new ones constantly. 2002-1593 was one of thousands. It was not the biggest, it was not the closest, It was not the brightest. It had no moon that anyone could see, no unusual colour, no strange orbit that demanded attention. It was, in every measurable way, an average member of its class, and its class was already considered the least interesting population in the solar system. If you had asked an astronomer in 2003 to rank the objects most likely to surprise us someday, this one would not have made the list. It would not have made any list. It was, for all practical purposes, a rounding error in a spreadsheet of the outer solar system. Let me give you a sense of just how small it is, because the size is going to matter enormously later, and I want it to be real to you, and not just a number. The best measurements we now have put its diameter at around 470 kilometres. That is a little under 300 miles across. Now, 300 miles sounds large when you imagine driving it, but on the scale of worlds it is tiny. Our own moon is about 3,470 kilometres across, which means you could line up roughly 7 of these objects side by side, and only just span the width of the moon. Compared to Pluto, which is the most famous resident of this part of the solar system, it is smaller still. Pluto is about 2,377 kilometres across, so 2002-1593 is only about 1/5 of Pluto's width, and Pluto itself, remember, was considered too small to keep its title as a planet. This object is 1/5 of that. If you shrank the Earth down to the size of a basketball, this little world would be smaller than a marble sitting next to it. Why does size matter so much? It comes down to gravity, and gravity is the thread that runs through this entire story, so it is worth slowing down on. Every object with mass pulls on everything around it. The more mass, the stronger the pull. A large world, like the Earth, has enough gravitational pull to hold onto a thick blanket of gas, our atmosphere, the air you're breathing right now. That air is made of molecules that are always moving, always jostling, always trying to fly off into space. The only reason they do not all escape is that the Earth's gravity is strong enough to hold most of them down. Now imagine a much smaller world, with much weaker gravity. The same restless gas molecules are still there, still moving, still trying to escape, but now the gravity holding them is feeble. The fastest molecules win. They reach what we call escape velocity, the speed at which gravity can no longer hold them, and they leak away into space, one after another, until eventually there is nothing left. The smaller the world, the easier it is for gas to escape, and the faster any atmosphere bleeds away into nothing. This is why, for a very long time, the rule seemed obvious and unbreakable. Big worlds can have atmospheres, small worlds cannot. A small world simply does not have the gravitational grip to hold gas in place over the long stretches of time we're talking about, the millions and billions of years that these objects have existed. Any gas they might once have had would have escaped to space ages ago, leaving behind a bare, airless surface. So an object like 2002-1593, 1/5 the width of an already small Pluto sitting out in the deepest cold of the Kuiper Belt, was assumed to be exactly what the rule predicted. Airless, a naked ball of frozen material with nothing between its surface and the vacuum of space. There was no reason to think otherwise. There was every reason, based on solid physics, to think the rule held. There is a particular family of these objects that 2002-1593 belongs to, and it is worth knowing about, because it ties this anonymous little world to the most famous resident of the outer solar system. The objects in this family are called Plutinos, which simply means little Plutos, and they are called that because they share something special with Pluto itself, a kind of gravitational relationship with the planet Neptune. Pluto, you may know, crosses inside the orbit of Neptune for part of its long journey around the Sun, and you might think that would eventually lead to a collision. But it never does, and the reason it never does is a beautiful piece of celestial clockwork called an orbital resonance. Here is how that resonance works. For every 2 times Pluto goes around the Sun, Neptune goes around exactly 3 times. 2 laps for Pluto, 3 laps for Neptune, locked together in a precise ratio, repeating over and over for billions of years. Because of that exact timing, Pluto and Neptune are choreographed so that they never come close to each other, even though their orbits cross. It is like 2 runners on a track whose paces are matched so perfectly that they are never at the same place at the same time, no matter how long the race runs. And 2002-1593 does the very same dance. It too goes around the Sun twice for every 3 times Neptune does. It too is held in that protective 2-3 rhythm. That is what makes it a Plutino, a small cousin moving to the same ancient beat that protects Pluto. Its orbit is not a perfect circle either, and the details matter for the story. It swings between about 34 astronomical units from the Sun at its closest and about 44 at its farthest, with the whole path tilted somewhat relative to the flat plane that most of the planets share. So it rises above and dips below the crowd, leaning out of the main traffic of the solar system. None of this made it stand out when it was found. There are many Plutonos. There are many tilted, mildly stretched orbits out there. It was simply one more entry, filed under a population that already had a famous member and a great many anonymous ones, and nobody had any reason to suspect that this particular anonymous one was keeping a secret that would force a chapter of the textbooks to be rewritten. It is worth knowing where objects like this fit in the wider bookkeeping of the solar system, because the category itself tells you how recently our picture of these worlds was assembled. Anything orbiting the Sun beyond Neptune is called, plainly enough, a trans-Neptunian object, which simply means an object across the orbit of Neptune from us. The first one other than Pluto was not even found until 1992, which is astonishingly recent when you think about it. For most of the history of astronomy, the region past Neptune was a blank, presumed mostly empty, with Pluto as its lone known inhabitant. Then better cameras and patient surveys began turning up object after object, and the blank filled in with a crowd. 2002, fit of 93, was one of those finds, discovered as the catalogue was swelling, just another faint mover added to a list that was growing faster than anyone could study its members. That history matters because it explains why so many of these worlds are little more than entries in a database. We have found a great many of them, far more than we have had time to examine in any detail. Most are known only as a position, an orbit, a rough size and brightness, and nothing more. They were spotted, catalogued, and then left alone, because there are only so many large telescopes and so many astronomers and so many nights, and the outer solar system holds more objects than we can possibly study one by one. 2002, 1593 sat in that vast unexamined backlog for more than 20 years, a name and an orbit and little else, until the chance alignment with a faint star finally gave someone a reason to look closely. And the moment someone did, it stopped being a database entry and became a mystery. And here is something that makes the whole thing even stranger before we have even gotten to the discovery. When astronomers later examined the surface of this object with the most powerful telescope ever sent to space, they found that its surface is mostly water ice, with some frozen carbon dioxide, and that it appears to be missing the very ices that on other worlds turn into atmospheres. On Pluto, there are ices of nitrogen and methane and carbon monoxide, the kinds of ices that can turn from solid straight into gas and feed a thin atmosphere. On this object, those ices were not detected on the surface at all, so not only was it too small to hold an atmosphere, it also seemed to be missing the raw materials to make one in the first place. By every line of reasoning we had, this was a world that should be sealed shut, frozen, finished, and silent. It was, you might say, the single most boring object in planetary science, which is exactly why what happened next was so impossible to ignore, because this boring little world was about to do something that none of the rules allowed. Part 3. The night the star did not blink. To understand what happened, you first have to understand a problem, and the problem is distance. 2002, 1593 is so far away and so small that we cannot simply take a picture of it. When you see a beautiful image of Jupiter or Saturn, with bands and storms and rings in crisp detail, you are seeing a world that is relatively close and relatively huge, reflecting a great deal of sunlight back to us. This object is the opposite of that. It is a fifth the size of Pluto, billions of miles away, sitting in light so dim that it is barely illuminated at all. Through even our best telescopes, it is not a world with features you can study. It is a faint point of light, a single pixel, a smudge that is hard to tell apart from the background. You cannot see its surface, you cannot see its shape, and you absolutely cannot see something as delicate as a thin layer of gas around it, not by looking at it directly. So if you wanted to know whether this object had an atmosphere, looking straight at it would tell you nothing. You would need a completely different trick. And astronomers have one, and it is one of the most elegant techniques in all of astronomy. The trick is called a stellar occultation, and the idea behind it is simple enough to explain in a single sentence, even though the execution is fiendishly precise. The idea is this: instead of looking at the object, you wait for the object to pass in front of a star, and you watch the star. Let me say that again, because it is the key that unlocks everything else tonight. You do not watch the object, you watch the star behind it. As the object drifts along its orbit, from our point of view it occasionally crosses directly in front of a distant star, blocking that star's light for a few seconds, the same way a person walking across a room can briefly block a distant streetlight from your view. When that happens, the star appears to wink out and then come back, and it turns out that the exact way the star winks out, the precise shape of that flicker, carries an astonishing amount of information about the object doing the blocking. Think about what happens if the object is a bare, airless rock. The star is shining steadily, a fixed point of light. The edge of the object sweeps across it. Because the rock has a hard, sharp edge and nothing around it, the starlight is cut off instantly, in a fraction of a second. One moment the star is there at full brightness. The next moment it is completely gone, snapped off like a switch. Then the object continues on its way, the far edge sweeps past, and the star reappears just as suddenly, snapping back to full brightness in an instant. A clean, sharp, instantaneous blink, off and on. That sharp edge is the signature of a world with no atmosphere, because there is nothing around the rock to interfere with the light. It is a knife-edge cut. Now think about what happens if the object has an atmosphere, even a very thin one. As the object approaches the star's light does not hit a sharp edge first. It first has to pass through the outermost thinnest layers of gas surrounding the object. Gas bends light. It bends it, and it dims it, gradually, the way a pencil looks bent when you put it in a glass of water. So as the edge of an object with an atmosphere approaches the starlight does not snap off. It fades. It dims gradually over a brief stretch of time as it filters through thickening layers of gas, growing softer and softer until the solid body of the object finally blocks it completely. And on the far side, the reverse happens. The starlight does not snap back. It swells gradually back into view, brightening through the layers of gas as the object moves away. A gradual fade in, a gradual fade out. Not a knife-edge blink, but a soft dissolve. And that soft dissolve, that gentle fading at the edges, is the fingerprint of an atmosphere. It is the one thing that gas does and bare rock cannot. So here is the situation. On the night of January 10th, in the year 2024, the orbit of 2002-1593 was going to carry it directly in front of a faint star, a star so dim you could never see it with your eyes, a star astronomers label as 15th magnitude, which is a way of saying it is thousands of times too faint to notice without a telescope. The path of this shadow, the narrow strip on the Earth's surface from which the object would appear to cross the star, happened to fall across Japan, and a team of astronomers led by Dr. Ko Arematsu of the National Astronomical Observatory of Japan made a plan to catch it. Catching an occultation is not a casual thing. The window is only a few seconds long. You have to know exactly where to point, exactly when, to a precision of seconds, and you have to hope the weather cooperates and the clouds stay away at that one critical moment. To improve their chances and to measure the object properly, they did not use a single telescope. They set up at 4 separate sites spread across the country so that the shadow would pass over several of them, and they could piece together its size and shape from the different vantage points. Now, I want you to be there for a moment, because this is one of those small, quiet moments where the history of a science turns and almost nobody notices it happening. Imagine the inside of one of those observatories late on a winter night. The dome is open to the freezing air. The telescope is locked onto a patch of sky that looks, to the eye, completely unremarkable, just a scattering of faint stars. On the screen, one particular faint star sits there, steady, its brightness being recorded many times every second, a number ticking by, holding level. The astronomers are watching that number. They are expecting, if anything happens at all, a clean blink. They are expecting the number to hold steady, then drop to nothing in an instant as the airless rock cuts off the light, then snap back a few seconds later. That is what a small dead Kuiper Belt object is supposed to do. That is what the rules say. The seconds tick down. The invisible shadow races across the Pacific, across the islands toward the telescope, and then it arrives. But the star does not blink. The number on the screen does not drop in an instant. Instead, it begins to slide. The starlight softens, dims, fades down over about a second and a half, smearing out where it should have been a clean cut. Then the star is gone, and a handful of seconds later, when it returns, it does not snap back either. It swells slowly into view, brightening gradually over another second and a half, easing back to full strength instead of flipping on like a switch. This technique of watching a star instead of the object has a history, and knowing a little of it helps you see why the team trusted what they found. Occultations have been quietly powerful in astronomy for a long time. They were how the rings of Uranus were discovered, back in 1977, when astronomers watching a star pass behind the planet saw it wink several times before and after the planet itself blocked it, betraying a set of rings nobody had seen. They have been used to measure the precise shapes of asteroids, to discover that some small bodies have rings of their own, and to map the sizes of distant worlds that no telescope could resolve. Even Pluto's own atmosphere, the only other atmosphere known out there before this, was studied in detail using exactly this method, watching how starlight faded as it passed through Pluto's thin air. So when the team set out to catch 2002-1593 crossing a star, they were using a tool with a long and trusted record, a tool that had surprised astronomers before. What makes the technique so demanding is the precision it requires. To predict that a particular object will pass in front of a particular star on a particular night, as seen from a particular narrow strip of the Earth, you have to know the object's orbit and position with extraordinary accuracy, and you have to know the star's position just as well. A tiny error in either one, and the shadow falls somewhere else entirely, perhaps over the ocean, perhaps over a different continent, and your carefully placed telescopes catch nothing but an ordinary star that never dims. The astronomers who do this work spend a great deal of effort refining their predictions, narrowing down exactly where the shadow will fall, so that observers can be placed in the right place at the right time. It is a kind of astronomical marksmanship, aiming not at the object but at the thin line its shadow will trace across the turning Earth. And then, even with a perfect prediction, you are at the mercy of the sky. The event lasts only seconds. There is no second chance that night. If a cloud drifts across the field at the critical moment, if the wind shakes the telescope, if a piece of equipment chooses that instant to fail, the event is simply lost, and the next chance may not come for years, until the object's wanderings bring it in front of another suitable star along a path you can reach. So every successful occultation is a small triumph of preparation meeting luck, of being ready, and being clear, and being pointed at exactly the right faint dot in the sky, at exactly the right second. The team had prepared for an ordinary result and were rewarded with an extraordinary one, which is so often how the best discoveries arrive, dressed as routine until the moment they are not. I want you to appreciate just how counterintuitive the whole method is, because it never stops being a little astonishing. You're not learning about a world by gathering more light from it. You're learning about it by watching it take light away. The information comes not from what the object gives you, but from what it withholds, from the precise manner in which it blocks a star that has nothing to do with it. A star perhaps hundreds or thousands of light years beyond it, that simply happens to lie along the same line of sight for a few seconds. The object and the star are utter strangers, unimaginably far apart, briefly aligned by chance and by the patient calculation of astronomers who knew the alignment was coming. And in that brief, accidental partnership, the distant star becomes a lamp held up behind the nearby world, and the way its light dims at the edges reveals the secret the world had kept for 4.5 billion years. For a moment, a thing like that does not register as enormous. It registers as wrong. A small wrongness in the data, the kind of thing your eye catches and your mind hesitates over. The edges are soft, the star faded instead of blinking, and then, as it sinks in, the small wrongness becomes one of the largest things you could possibly find, because there is only one thing in nature that softens the edge of a star that way. There is only one explanation for light that fades instead of cutting. Something was wrapped around that little world. Something was bending the starlight as it passed. There was gas out there, a layer of atmosphere clinging to an object that, by every rule we trusted, had no business having one at all. The star did not blink. It faded. And in that faint, slow flicker of light, on a cold night in January, the frozen graveyard rolled over in its sleep. Part 4. Reading a World in 18 Seconds. Let me slow down and show you just how much those few seconds actually told the astronomers, because it is genuinely remarkable that so much can be read from so little. At the site at the Kiso Observatory, run by the University of Tokyo, the star was blocked for about 16.5 seconds. At another site near Kyoto, the star was blocked for about 18 seconds. That difference is not a mistake, it is a measurement. The two telescopes were looking through slightly different parts of the shadow, the way two people standing a few feet apart see a passing car block, a distant light for slightly different lengths of time depending on their exact line of sight. By comparing how long the star was blocked at each location, and knowing exactly how fast the object was moving along its orbit, you can work backward and calculate the width of the object itself. That is how we know its size as well as we do. The figure that comes out is a radius of around 235 kilometers, give or take, which is to say a diameter of around 470 kilometers, assuming the object is roughly round. A world measured not by photographing it, but by timing how long it took its shadow to cross a star. There is something almost unbelievable about that when you sit with it. We have never seen this object as anything more than a point of light, and yet we can tell you how wide it is to within a few tens of kilometers because of 18 seconds of a star going dark. But the size was not the surprise. The surprise was in the edges, in that gentle fade I described, and the team had it recorded at more than one site, which matters enormously. A single telescope catching a strange signal is interesting but fragile. Maybe a thin cloud drifted past at the worst possible moment. Maybe the instrument hiccuped. Maybe a gust of wind shook the telescope and smeared the light. Any of those things could, in principle, make a clean blink look like a soft fade if you only saw it once, from one place. But the gradual dimming showed up at the sites that recorded the full event, on both the way in and the way out, in a consistent and symmetric way that a passing cloud or a random glitch would not produce. And then there was a fourth site, in Fukushima, that turned the whole thing from convincing into nearly airtight. At that location, the object did not pass squarely in front of the star. It was a near miss. The solid body of the object never fully covered the star from that vantage point, and yet, from Fukushima, they still recorded a dimming of the starlight, a softening, even though the star was never fully blocked. Think about what that means. The solid rock missed the star from that angle, but something still dimmed the light. The only thing that could do that is a layer of gas extending out beyond the solid edge of the object, a layer wide enough to brush across the star even when the rock itself did not. That fourth site caught the atmosphere alone, with no occultation behind it, and in doing so it confirmed that the fading really was coming from gas around the object, and not from some trick of one particular telescope. So put the pieces together, the way the team did in the weeks and months after that night. You have an object whose size you have now measured, about 470 kilometers across. You have a soft fade in the starlight, recorded at multiple sites, on both ingress and egress, symmetric and consistent. You have a fourth site that caught the atmospheric dimming even on a near miss. There is really only one conclusion that survives all of that evidence together. This little world, this anonymous fragment of the Kuiper Belt, this object that by every rule should have been a bare frozen rock, is wrapped in a thin shell of gas. It has an atmosphere, and not just any atmosphere in any ordinary place. This is the first time in history that anyone has detected an atmosphere around a trans-Neptunian object other than Pluto. For decades, Pluto stood alone out there as the one body past Neptune known to wear even a wisp of air. Now there are two, and the second one is a fraction of Pluto's size, which is precisely what makes it so hard to explain. I should be careful and honest about what kind of atmosphere we're talking about, because if you are picturing anything like the air around you, you are picturing it far too thick. This atmosphere is almost nothing. When the team worked out how much gas there must be to produce the fading they saw, they arrived at a surface pressure of somewhere between 100 and 200 nanobars. A nanobar is a billionth of a bar, and 1 bar is roughly the air pressure at sea level on Earth. So this atmosphere is on the order of 5 million to 10 million times thinner than the air you're breathing. Let me try to make that comparison land, because numbers that large stop meaning anything if you just say them. If the Earth's atmosphere were the depth of an ocean, this atmosphere would be thinner than the faintest film of mist left on a window after your breath fades from it. It is technically a gas, technically an atmosphere, but it is so close to being nothing that for most of human history we would have had no way to detect it at all. Even compared to Pluto, which already has one of the most fragile atmospheres we know of, this one is something like 50 to 100 times thinner still. It is the faintest possible whisper of an atmosphere, a breath, almost, rather than a sky. It is worth pausing on how strange and wonderful it is that timing alone can measure a world. Everything the astronomers learned about the size of this object came from comparing how long the star stayed hidden at different sites. Light travels in straight lines, and the object casts a shadow of itself onto the Earth, and that shadow sweeps across the ground as the object moves. A telescope sitting in the middle of the shadow's path sees the star blocked for the full width of the object. A telescope near the edge of the path sees it blocked for a shorter time, because the shadow only clips it. By collecting the durations from several telescopes spread across the shadow's track, you can reconstruct not just how wide the object is, but something of its shape, whether it is round or flattened or irregular. From a few seconds of darkness recorded at a handful of sites, a whole world takes form on paper, and the gradual fade carries even more than the simple fact of an atmosphere. The exact way the starlight dims, how quickly it falls, how the curve of brightness bends as the edge of the gas crosses the star, encodes information about how thick the atmosphere is and how its density changes with height. That is how the team arrived at their estimate of the surface pressure, that figure of 100 to 200 nanobars. They did not measure the pressure directly, they inferred it from the precise shape of the fading by comparing the real light curve against models of how atmospheres of different thicknesses would bend and dim the starlight passing through them. The number came out of the curve, the way the size came out of the timing. It is detective work of the highest order, reconstructing the properties of an invisible shell of gas around an unseeable world from nothing but the changing brightness of a star behind it. I want to underline what a milestone this is, because it is easy to let it slip past in the flood of detail. For the entire history of the study of the outer solar system, Pluto stood alone. It was the one object beyond Neptune that we knew had an atmosphere, the single exception in a region full of worlds we assumed were bare. Generations of astronomers grew up with that fact, Pluto and only Pluto. And now, with 18 seconds of a fading star recorded from a few telescopes in Japan, that lonely fact has a companion. The count has gone from 1 to 2. And the second member of this exclusive club is not a grand world like Pluto. It is a small, anonymous fragment a fifth of Pluto's width, which means the door that was thought to be open only to large worlds has just been shown to admit small ones too. A single new member can change the meaning of an entire category, and this one does. And yet that whisper is the entire point. Because the rule was never that small worlds have thin atmospheres. The rule was that small worlds, this small, this cold, this far away, have no atmosphere at all. None. Zero. A bare surface against open space. The discovery is not that the atmosphere is thick. The discovery is that it exists. It is the difference between zero and not zero, and in science, the difference between zero and not zero is sometimes the difference between everything we thought we understood and everything we are about to learn. The team had found the impossible thing. Now they had to face the much harder question, the one that has kept this discovery alive in conversations among planetary scientists ever since. Not whether the atmosphere is there. They are confident it is there. The question is how. How can a world this small, this cold, and this poor in the right ingredients possibly have an atmosphere at all? And to feel the full weight of that question, we have to look at exactly why it should be impossible, because it is not impossible for one reason. It is impossible for 3. Part 5. 3 impossibilities. When scientists call something impossible, they usually mean it politely. They mean it violates what we currently understand, that it sits outside the rules as we have written them. And the atmosphere on 2002-1593 is impossible in that strong sense. Not for a single reason, but for 3 separate reasons that stack on top of one another. Each one alone would be a puzzle. Together, they form a wall. Let me take you through them one at a time, slowly, because understanding why this should not be possible is the only way to feel how strange it is that it is. The first impossibility is the one we have already touched on. The object is too small to hold gas. We talked about gravity, about how a small world has only a weak gravitational grip, and about how gas molecules are always in motion, always trying to escape. On a world this size, the math is not kind to atmospheres. The gravity is so feeble that gas molecules, especially when they are warmed even slightly and start moving faster, can reach escape velocity and drift away into space without much trouble at all. An atmosphere on a body this small is like trying to hold sand in an open hand while walking through wind. It leaks, it thins, it goes. And over the enormous stretches of time involved, the millions and billions of years this object has existed, Any atmosphere it had should have leaked away completely a long, long time ago. There should be nothing left. The fact that there is something left, right now, today, is the first thing that should not be. The second impossibility is about temperature, and it is a little more subtle, so let me build it carefully. Suppose you set aside the leaking problem for a moment and ask a simpler question. Even if this world could somehow hold an atmosphere, where would the gas come from in the first place? An atmosphere is not free. It has to be made of something, and that something has to get into gas form somehow. On Pluto, the mechanism is understood. Pluto has ices on its surface, nitrogen ice and methane ice and carbon monoxide ice, and these are what we call volatile ices, meaning they turn into gas easily. When Pluto swings closer to the Sun in its long orbit, the faint sunlight is just barely enough to warm these ices and turn some of them directly from solid into gas, a process called sublimation, the same process that makes dry ice steam in the open air. That sublimated gas becomes Pluto's atmosphere, and when Pluto swings away from the Sun again, it cools, and the gas freezes back onto the surface as ice, and the atmosphere partly collapses. It is a slow seasonal cycle, breathing in and out over 248 years. But here is the problem for our little world. It is far too cold for this to work. Its surface sits at only about 40 to 50 degrees above absolute zero, around minus 380 degrees Fahrenheit. At that temperature, the main ices we know are on its surface. Water ice and frozen carbon dioxide do not sublimate. They cannot. They are locked solid, far below the temperature at which they would turn to gas. The Sun out here is simply too weak to lift them. So even if the world could hold an atmosphere, the obvious way to make one, sunlight warming surface ice into vapor, does not function at these temperatures. The furnace is off. And then comes the third impossibility, which is in some ways the strangest of all, because it removes the last easy escape from the puzzle. You might say, all right, maybe it does have some volatile ices, some nitrogen or methane like Pluto, and maybe those sublimate even at this temperature in small amounts. It would be a stretch, but maybe. Except we looked. The James Webb Space Telescope, the most powerful eye humanity has ever placed in space, examined the surface of this object, in observations spread across 2022 and 2024, and it read the chemistry of that surface by the light it reflects. And what it found was water ice, and some frozen carbon dioxide, and crucially, no detectable methane, no detectable nitrogen, no detectable carbon monoxide. The very ices that feed Pluto's atmosphere, the volatile ones that could turn to gas and supply a sky, were not seen on the surface at all. So the world is not only too small to hold an atmosphere and too cold to sublimate the ices it has, it also appears to be missing the specific ices that on every other world are the source of an atmosphere in the first place. The cupboard is bare. Let me make the gravity problem concrete, because it is the foundation everything else rests on. On any world, the gas molecules of an atmosphere are in constant motion, and the warmer the gas, the faster they move. There is a certain speed, set by the world's gravity, called the escape velocity, and any molecule moving faster than that in the right direction will simply fly off into space and never come back. On the Earth, the escape velocity is high, about 7 miles every second, far faster than ordinary air molecules move, which is why our atmosphere stays put. On a world a fifth the width of Pluto, the escape velocity is tiny by comparison. The gravitational grip is so gentle that even the slow, cold molecules out here can, over time, dribble away into space. There is no violent stripping required, no dramatic event. The atmosphere simply seeps away, molecule by molecule, like water leaking from a cupped hand, until none is left. Over the millions and billions of years available, that leak should have run completely dry long ago. The temperature problem deserves the same care, because it is not obvious why cold should prevent an atmosphere, and the reason is subtle and important. An atmosphere has to be supplied from somewhere. The natural supply on a frozen world is sublimation, the process by which a solid ice turns directly into gas without ever becoming a liquid, the way a block of dry ice gives off vapor, or the way snow can slowly vanish on a cold sunny day without melting. But sublimation needs at least a little energy, a little warmth, to lift the molecules off the ice and into the gas. Each kind of ice has its own temperature at which it begins to sublimate appreciably. Water ice and frozen carbon dioxide need it relatively warm by these standards. At the 40 to 50 degrees above absolute zero that reign on this world, they stay locked solid, immobile, unable to feed any sky. The The sun out here simply cannot supply the energy needed to lift them. The furnace that drives Pluto's seasonal atmosphere, faint as that furnace is fainter still here, too faint to light at all. And then there is the matter of the missing ingredients, which I keep returning to because it is the part that closes off the easiest escape. You might reasonably say, fine, water and carbon dioxide ice will not sublimate at these temperatures, but what about the more volatile ices, the nitrogen and methane and carbon monoxide that do turn to gas more readily, even in the cold? Those are exactly the ices that feed Pluto. And the answer, from the most powerful telescope ever built, is that they do not appear to be on the surface of this world at all. The James Webb Space Telescope examined the light reflected from the surface, which carries the chemical fingerprints of whatever ices are present, and it read water ice and some frozen carbon dioxide, and it did not find the volatile ices. So the obvious sources of gas are absent. The world is not only too small and too cold, it appears to lack the very materials from which an atmosphere is usually built. 3 walls, all standing, and an atmosphere on the other side of them anyway. There is a way of feeling these 3 impossibilities together that I find clarifying, so let me offer it. Imagine you're told that a candle is burning in a sealed room. Your first thought might be that someone must have lit it, that there must be a flame and a wick and a supply of wax. Now imagine you're told 3 further things. First, the room has no door or window through which anyone could have entered to light it. Second, the room is so cold that wax cannot melt and a flame cannot catch. And third, when you finally look inside, there is no wax in the room at all. Nothing for a candle to be made of. And yet, through the keyhole, you can plainly see a soft light flickering. That is the situation the astronomers are in. The light is real. They have seen it, measured it, confirmed it from several angles, but every ordinary way the light could come to be is ruled out. No door, too cold, no fuel, and the flame burns anyway. When you're in a situation like that, you do not get to simply deny the light. The light is the data, and the data is solid. What you have to do instead is question your assumptions about the room. Maybe there is a hidden door you have not found. Maybe there is a source of warmth you did not account for. Maybe the fuel is there but hidden, buried where you could not see it. Or maybe it is a kind of fuel you did not think to look for. Each of those corresponds to a real scientific possibility for our little world, a hidden internal heat source, a buried supply of ice, a recent delivery from outside. The impossibility is not a wall that ends inquiry. It is a sign pointing at exactly which of our assumptions must be wrong and inviting us to find out which one. That is what makes an impossible result so valuable. It does not tell us we have failed. It tells us, with great precision, where to dig. Sit with all 3 of those at once, because that is where the genuine strangeness lives. Too small to keep gas, too cold to make gas, missing the ingredients that gas is usually made from. Any one of these on its own you might wave away with a clever idea. But all 3 together build a situation where, by the rules as we understand them, there should be no atmosphere by any route we know. The gas should have escaped. It should not have formed. There should not even be the right material to form it. And yet the starlight faded. And yet the gas is there. This is what it actually looks like when nature breaks a rule. It is not loud. There is no explosion, no flash. It is a quiet contradiction, a fact sitting calmly in a data set that should not be able to exist, looking back at the scientists who found it and refusing to go away. When you have 3 independent reasons that something is impossible, and it happens anyway, there are only 2 possibilities. Either you got the measurement wrong, or you got the rules wrong. The team checked the measurement very carefully from 4 sites, with a near miss to confirm it. The measurement holds, which means, somewhere in our confident understanding of these small frozen worlds, we got the rules wrong, and the rest of this story is the search for exactly where. Part 6. The World That Might Be Alive. When you're faced with an impossible thing that is nonetheless real, the work begins of finding the loophole, the hidden assumption, the thing you took for granted that turns out not to be true. Aramatsu and the team proposed 2 possible explanations for where this atmosphere could be coming from, 2 ways the impossible could become merely surprising. They are very different from each other, and they lead to very different pictures of what this little world actually is. We're going to spend real time with both, because the choice between them is the live question, the thing that has not been settled, the part of this story that is still being written right now. The first explanation is the more startling of the 2, because it would mean that this object which we filed away as dead is in some sense alive. Not alive in the way you are alive, not biology, but alive in the way a planet is alive, with heat and motion and activity going on inside it. The word for the mechanism is cryovolcanism, and it is worth understanding properly because it is one of the more wonderful ideas in planetary science. You already know what an ordinary volcano is. Somewhere beneath the surface of the Earth, rock gets hot enough to melt, becoming magma, and that molten rock is buoyant and full of dissolved gas, so it forces its way upward through cracks and weaknesses until it bursts out at the surface as lava. A volcano is the planet's interior heat finding a way out. Now take that same idea and move it to a world made not of rock but of ice. Out in the cold of the outer solar system, the role that rock plays on Earth is played by ice, and the role that molten rock plays is played by liquid water, or by even more exotic mixtures, water laced with ammonia, slushes of different ices that melt at lower temperatures. A cryovolcano is an ice volcano. Instead of erupting hot molten rock, it erupts cold liquid water or icy slush from beneath a frozen crust, and when that material reaches the surface, where the pressure is almost nothing, the volatile parts of it can flash into gas. If something like that is happening on 2002-1593, then the atmosphere is not a relic at all. It is being actively produced, vented from inside the world through cracks and openings, fed continuously from below. The gas that the starlight revealed would be, in effect, the breath of a world that never actually died. If that is true, it is staggering, and you should let yourself feel why. It would mean that this tiny object, only a few hundred kilometers across, billions of years old, sitting in the absolute cold of the Kuiper Belt, still has warmth inside it. It still has activity. It still has, somewhere beneath that frozen shell, enough energy to push material up and out. And that runs directly against one of our oldest assumptions about small worlds, which is that they cool off quickly and stay cold. The reasoning was always that big worlds, like the Earth, hold their internal heat for billions of years because they are large, and large things lose heat slowly relative to their volume, the way a large pot of soup stays warm far longer than a small cup. Small worlds, by that logic, should have given up their heat long ago and frozen solid all the way through. A 470-kilometre ball of ice should be, by now, a cold dead thing from its surface to its centre. So if it is venting gas from inside, then something is keeping it warm that we did not account for, and our model of how long small worlds stay active is simply wrong. That is not a small correction. That would touch how we think about a whole population of objects, not just this one. And I want to stress that cryovolcanism out here is not a wild invention dreamed up to rescue this one observation. We have seen it, or something very like it, in this part of the solar system before, which is exactly why scientists can propose it with a straight face. Consider Triton, the large moon of Neptune. When the Voyager 2 spacecraft flew past Triton in 1989, it photographed dark streaks on the surface and caught what appeared to be geysers, plumes of nitrogen gas erupting several kilometers up from the surface, carrying dark material with them. Triton, a frozen world in the outer solar system, was active. Consider Pluto itself, which we now know far better than we used to. Pluto has features that look very much like cryovolcanoes, two great rises called Wright Mons, and Picard Mons that many scientists think were built by icy material welling up from below. And consider Makemake, another dwarf planet of the Kuiper Belt, where astronomers have detected signs of methane gas, possibly being outgassed from the surface. So the idea that a frozen world out here can release gas, can be active, can have some internal life to it, is not new. What would be new, what would push the idea further than it has ever gone, is finding it on something this small. Triton is a large moon. Pluto and Makemake are dwarf planets. 2002-1593 is a fraction of their size. To find activity here would be to extend the club of living worlds to a member so small that nobody thought to invite it. Let me take you to Triton for a moment, because it is the best evidence we have that frozen worlds out here can be active, and seeing it makes the whole idea feel less like a guess. In the late summer of 1989, the Voyager 2 spacecraft, having already visited Jupiter and Saturn and Uranus, made its final planetary encounter, sweeping past Neptune and its large moon Triton. Nobody knew quite what to expect. Triton is a cold world, far from the sun, the kind of place that should, by the old reasoning, be dead and still. Instead, the images that came back showed a surface unlike anything seen before, with strange terrain that looked like the skin of a melon, and, most startling of all, dark streaks that appeared to be the fallout from active geysers. Triton was venting nitrogen gas, in plumes that rose several kilometres above the surface before the faint winds smeared their dark material downwind. A frozen moon, far out in the cold, was actively erupting. The lesson stuck. The outer solar system was not necessarily as dead as it looked. Pluto reinforced that lesson decades later, when the New Horizons spacecraft flew past it in 2015 and revealed a world astonishingly full of activity for something so cold. There were mountains of water ice standing thousands of feet tall, frozen plains that appeared to be slowly churning and renewing themselves, and two enormous rises, named Wright Mons and Picard Mons, that many scientists interpreted as cryovolcanoes, places where icy material had welled up from below and built great structures on the surface. Pluto, like Triton, refused to be the dead rock it was supposed to be. And then there is Makemake, another dwarf planet of the Kuiper Belt, where astronomers detected signs of methane gas that may be seeping from the surface. So the pattern repeats across the outer solar system. Again and again, when we look closely at a frozen world out there, we find that something is still happening, that the cold has not entirely won, that there is more going on beneath the ice than the old picture allowed. What none of these examples fully solves is the engine problem, the question of where the heat comes from, and this is the honest frontier of the whole idea. Triton may be flexed by Neptune's gravity, since it orbits a giant planet on an unusual path. Pluto is much larger than our little world, and had more heat to begin with hints of a buried reservoir of liquid kept warm by the slow decay of radioactive elements in its core. But 2002 5093 is small, and it orbits no giant planet that could squeeze and flex it. So if it is genuinely active, the source of its warmth is a real puzzle. Perhaps there is more leftover heat in small bodies than we assumed. Perhaps some chemical process, some slow release of energy locked into the ice itself plays a role. Perhaps the answer is something we have not thought of at all. The team is honest about this gap, and the gap is not a reason to dismiss the idea so much as a sign that, if the idea is right, we have been wrong about something basic in how these small worlds hold and lose their warmth. There is, of course, the obvious objection. The thing your own mind is probably already raising, and it is the right objection. What could possibly keep something this small warm enough to be active after 4.5 billion years? On Earth, the internal heat comes partly from the slow decay of radioactive elements buried in the rock, and partly from heat left over from the planet's violent formation. On some moons, like Europa around Jupiter, the heat comes from tides, from being flexed and squeezed by the gravity of a giant nearby planet, which generates friction inside. But 2002 1593 has no giant planet next door to flex it. It is out on its own. And it is small, so whatever radioactive heat it started with should have faded. This is the honest weak point of the cryovolcanism idea, and the team does not hide it. They do not know what would power the activity. It is a hypothesis with a missing engine. But notice that the missing engine is not a reason to throw the idea out. It is a reason to take it seriously, because if the activity is real, and we cannot identify the engine, then we are missing something fundamental about how these worlds work, and that, in a way, is the most exciting kind of problem there is. The kind where the universe is plainly doing something, and we have to admit we do not yet know how. But cryovolcanism is not the only explanation on the table. There is a second one, and it is stranger and sadder, and it turns on the idea that we might be looking at something that is not going to last. Part 7. A single breath. The second explanation does not require the world to be alive at all. It requires the world to have been struck. The idea is this. Out in the Kuiper Belt, objects are not perfectly alone. They drift in enormous slow orbits, and very occasionally, on timescales of millions of years, one of them crosses paths with another, and they collide. The outer solar system is mostly empty, so these collisions are rare, but rare is not the same as never. And over the long history of the solar system, every object out there has likely been hit at some point. So suppose that, sometime in the relatively recent past, a comet or a smaller icy body struck 2002 1593. An impact like that delivers an enormous amount of energy in an instant. It can vaporize ice on the surface, turning solid into gas in a flash. It can dig down and expose fresh material from below. And the impactor itself, if it was an icy body, brings its own volatile material along with it. The result of such a collision could be a sudden release of gas, a temporary cloud that settles into a thin atmosphere around the object. Under this explanation, the atmosphere is not the breath of a living world, it is the smoke after a crash. It is debris, suspended briefly, in the process of drifting away. And that phrase, drifting away, is the heart of this second idea, because it carries a consequence that I find genuinely haunting. Remember the first impossibility, that this world is too small to hold gas, that any atmosphere it has should leak away into space. Under the cryovolcanism explanation, that leaking is balanced by constant resupply from inside, so the atmosphere persists. But under the impact explanation, there is no resupply. The gas was delivered once, in a single event, and now it is simply leaking, with nothing replacing it. And in this object's weak gravity, the leak is not slow on cosmic terms. The calculation suggests that an atmosphere produced this way would bleed off into space and vanish completely within something like 1,000 years. 1,000 years. On the scale of a world that is 4.5 billion years old, 1,000 years is nothing. It is less than the blink of an eye. It is a single breath drawn and released. I want you to sit inside that timing for a moment, because it leads somewhere that is hard to look at directly. Here is a world that has existed for 4.5 billion years. For almost the entirety of that time, by this explanation, it had no atmosphere at all. It was exactly what we assumed, a bare frozen rock, silent and airless, for billions upon billions of years. And then, at some point in just the last few centuries, something hit it, and for one brief geological instant, a thin shell of gas wrapped around it, an atmosphere that will be gone again before very long. And in that tiny sliver of time, that one moment out of billions of years when this object happens to have an atmosphere, we happen to be alive, and we happen to have built telescopes capable of seeing it, and we happen to point them at exactly this faint star on exactly the night that this little world passed in front of it. Think about the odds of that. Out of 4.5 billion years of nothing, we caught it during the few hundred years it has something. It is like walking into a darkened theatre, in a film that runs for the entire age of the universe, and arriving in your seat during the one frame that is not black. Imagine that you could stand outside this world and watch its entire life played back at enormous speed, 4.5 billion years compressed into a single hour. For 59 minutes and 59 seconds, you would see nothing change at all. A grey ball of ice, turning slowly in the dark, the sun a distant point that never warms it, the surface unmarked and unmoving, age after age after age of perfect frozen stillness. And then, in the final fraction of the final second, you would see it suddenly veiled, for the briefest moment, in a thin haze of gas, there and then already fading, already leaking back into the black. That fraction of a second is the moment we live in. That is our window. If the impact explanation is correct, then everything we are talking about tonight exists only because we are watching during that single flicker. And if humanity had come along a few thousand years later, we would have found exactly the dead rock we expected, and never known that for one moment it breathed. There is something almost unbearably poignant in that. The idea that the universe is full of brief events like this, flaring and fading, and that to witness even one of them requires being the right kind of creature, with the right kind of instruments, paying attention at the right moment. We are not just lucky to have found this. We are lucky to exist in the narrow band of time when finding it was possible at all. Collisions in the Kuiper belt are worth understanding properly, because the whole second explanation rests on one having happened recently, and your intuition about how crowded space is will probably mislead you. The Kuiper belt contains an enormous number of objects, hundreds of thousands of sizable ones and countless smaller fragments, and so you might imagine it as a crowded field where crashes are constant. But the region is also unimaginably large, a thick ring billions of miles across, and the objects are spread so thinly through that immense volume that they almost never meet. If you stood on the surface of our little world and looked around, you would see no other object at all, just empty black sky in every direction, the nearest neighbour likely millions of miles away. Space out here is mostly, overwhelmingly, nothing. So collisions are rare, exceedingly rare, separated by vast stretches of time, but rare is not never, and over 4.5 billion years, even rare events add up. Across that immense span, essentially every object out here has probably been struck at some point, chipped or cratered or shattered by an encounter with another body. The question is not whether 221593 has ever been hit. It almost certainly has many times over the eons. The question is whether it has been hit recently, in just the last handful of centuries, recently enough that the gas from the impact has not yet finished leaking away. And that is where the coincidence becomes hard to swallow, because recent collisions, on the scale of 1,000 years out of 4.5 billion, are extraordinarily uncommon for any single object. To have one happen, and to have humanity arrive and look at exactly the right moment to catch the fading aftermath, stacks one unlikely thing on top of another. This is the genuine tension that keeps the two explanations in balance, and I think it is worth feeling rather than resolving too quickly. The impact explanation does not require us to rewrite our understanding of how small worlds hold heat. It is, in that sense, the more conservative idea, asking only that a rare collision happened. But it demands an uncomfortable amount of luck, that we are watching during a vanishingly brief window. The cryovolcanism explanation demands no luck at all, since an actively replenished atmosphere could persist for ages, and we would find it whenever we looked. But in exchange, it asks us to accept that a tiny ancient world is still warm and active in a way our models cannot explain. So you must choose your discomfort. Either the universe handed us a coincidence of remarkable size, or it handed us a world that should be dead and is not. Neither is comfortable. Both are possible, and that more than any single fact is what makes this discovery feel so alive, the sense that the universe has set us a genuine puzzle with no easy way out. It helps to know what a comet actually is, because if a collision delivered this atmosphere, a comet is the most likely culprit, and comets are stranger and more relevant than they first appear. A comet is essentially a dirty snowball, a loose mixture of various ices and dust left over, like the Kuiper Belt objects themselves, from the formation of the solar system. Many comets come from this very region, or from even farther out, and they are rich in exactly the volatile materials, frozen gases and ices, that our little world seems to lack on its own surface. So if a comet, or a comet-like fragment, struck 221593, it would not only blast gas off the surface by the sheer energy of the impact, it would also deliver its own cargo of volatile ices, fresh material that could vaporize and contribute to a temporary atmosphere. In that sense, the impact explanation neatly sidesteps the missing ingredients problem. The world does not need to have had the right ices itself, if a passing comet brought them along and left them behind in a violent instant. But the same explanation that solves one problem sharpens another, and that is the timing. Whatever gas an impact delivers, the world is still too small to hold it, so it begins leaking away immediately, and within something like 1,000 years it should be gone entirely. This means the impact, if there was one, had to be recent, geologically speaking, a blink ago in the life of a world billions of years old. And recent impacts for any single object in the thinly populated outer solar system are rare almost to the point of improbability. So the impact explanation asks us to believe in a rare event that happened to occur in the very recent past, and that we happen to catch in the act. It is not impossible. Rare things do happen, and someone has to be the one to witness them. But it requires accepting a chain of fortunate timing that grows less comfortable the longer you look at it, which is exactly why the alternative, the quietly active world, refuses to go away. And maybe that is too much luck to believe. That is the honest tension at the centre of this explanation. If the atmosphere is a fleeting thing that lasts only 1,000 years, then catching it requires a coincidence so large that some scientists find it hard to swallow, and reasonably so. A coincidence that big is itself a kind of argument against the explanation, because the universe does not usually arrange for us to arrive at exactly the right instant. Which is part of why the other explanation, the living world quietly venting gas for ages, remains so attractive, because it does not require us to be lucky. If the world is actively producing its atmosphere, then it has probably had one for a long time and will have one for a long time to come, and our catching it is no coincidence at all. So we have two stories. In one, the world is alive, and we were always going to find its breath whenever we looked. In the other, the world was struck, and we are witnessing the last exhalation of a brief and dying event that we were astonishingly fortunate to see. Both fit the data we have. Both are possible, and the remarkable thing, the thing that makes this not just a mystery but a solvable one, is that the universe is going to tell us which is true. We just have to keep watching. Part 8. How we will know. Here is what I love about where this story sits right now. It is not a mystery that ends in a shrug. It is not one of those questions that we can only argue about forever without hope of an answer. There is a clean, almost beautifully simple test that will distinguish between the two explanations, and the test comes down to a single question. Is the atmosphere staying the same, or is it fading? That is it. That is the whole key. Because the two explanations make opposite predictions about what will happen next, and all we have to do is watch carefully enough, for long enough, to see which prediction comes true. Think it through with me. If the atmosphere comes from a recent impact, then it is leaking away with no resupply, and that means it is getting thinner over time. Slowly, year by year, decade by decade, there should be less gas, lower pressure, a fainter and fainter signature when the object next passes in front of a star. So if astronomers monitor this world over the coming years and find that its atmosphere is steadily decreasing, growing weaker, draining away, then that points strongly toward the impact explanation. We would be watching the smoke clear after the crash, in real time. On the other hand, if the atmosphere comes from cryovolcanism, from active venting inside the world, then it is being constantly replenished. The gas that leaks away is replaced by new gas pushing up from below, and the atmosphere should hold roughly steady. So if astronomers monitor this world and find that its atmosphere stays the same, year after year, neither growing nor fading, then that points toward an active, living world, topping up its own sky from within. Decreasing means dying. Steady means alive. It really is almost that simple, and the elegance of it is that nature itself will provide the answer if we are patient enough to keep our eyes on it. There is a second line of investigation too, and it involves the most powerful telescope we have. The James Webb Space Telescope can do more than photograph surfaces. It can read the chemistry of light, splitting it into its component colors and identifying the fingerprints of specific molecules. If Webb can be brought to bear on this atmosphere, it could tell us what the gas is actually made of, and that would be a major clue. Remember that the surface seems to be missing the usual volatile ices, the nitrogen and methane and carbon monoxide. So what is the atmosphere made of? One possibility scientists have raised is that it could be made of other light gases that are harder to detect on the surface, perhaps nitrogen or even argon, gases that might be present in ways we have not yet measured. Another possibility is that there is methane after all, but confined very close to the surface in a way that the earlier observations did not catch. Knowing the composition would narrow the field. Certain compositions would fit better with an impact, others with internal activity. The chemistry is a second thread that, pulled carefully, helps unravel the same knot. There is something deeply characteristic of science in this situation, in the way the answer is not declared but awaited, and I think it is worth dwelling on because it runs against how we usually imagine discovery. We tend to picture science as a series of triumphant announcements, a finding revealed, a mystery solved, a curtain pulled back, but far more often, real science looks like this: a careful question, two competing answers, and a patient plan to let the evidence accumulate until one answer wins. The team that found this atmosphere did not rush to claim they knew its origin. They laid out both possibilities honestly, named the weakness in each, and described exactly what future observations would settle the matter. That restraint is not a failure of nerve. It is the discipline at the core of the whole enterprise, the willingness to say we do not yet know, and here is precisely how we will find out. The monitoring itself will take time, and that time is part of the story. To measure whether the atmosphere is thinning, astronomers need to catch this object occulting other stars in the years to come, and each such event requires the same demanding combination of accurate prediction, good placement, and clear skies that made the first one possible. So the answer will not arrive next week or perhaps even next year. It will be assembled slowly, occultation by occultation, as the object wanders in front of new stars and new networks of telescopes catch it fading, and the measured pressure is compared against that first value of 100 to 200 nanobars. If, over a span of years, that pressure is seen to drop, the case for a recent impact strengthens. If it holds steady, the case for active replenishment grows. The universe will answer, but on its own slow schedule, and we will have to wait. And the chemistry, read by the great telescope in space, may speak sooner and add its own voice to the question. If the composition of the atmosphere can be pinned down, it would tell us a great deal. An atmosphere rich in some particular gas might point clearly toward a buried source within the world, while a different mixture might better fit material delivered or vaporized by a collision. Every piece of evidence narrows the possibilities, closes off some explanations, strengthens others. This is how a mystery like this actually gets solved, not in a single stroke, but by patient triangulation from several directions at once, the occultations measuring the pressure over time, the telescope reading the composition, the theorists modelling what each result would imply. Slowly, the space of possible answers contracts, until what remains is the truth, or the closest approach to it that the evidence allows. We are in the middle of that process right now, and that is a privilege, because we get to watch a real scientific question being settled in real time, instead of simply being handed the finished answer. It is worth saying plainly that the people who do this work may not be the ones who see it finished, and they do it anyway, which tells you something about the spirit of the whole enterprise. The monitoring could take years, perhaps many of them, before the trend in the atmosphere is clear enough to settle the question, and even then, fully understanding what is happening on this world, what powers it, what it is made of, may take a generation or more of patient observation with instruments not yet built. The astronomers laying the groundwork now are planting seeds whose fruit they may never taste, contributing pieces to an answer that will be assembled long after the first discovery has become an old story. That is how science actually moves forward, not in single triumphant leaps by lone geniuses, but as a long relay, each generation carrying the question a little further and handing it on. The flicker of a star on a winter night in 2024 is one leg of a race that will run for decades, and the people running it now are content to run their part well and pass the baton, trusting that the answer, when it finally comes, will have been worth the wait. What strikes me about all of this is that it places us at a very particular moment in the life of a discovery. We are past the first shock. We know the atmosphere is there, but we are before the resolution. We do not yet know which story is true. We are in the middle of the investigation, in that suspended stretch where the question is fully formed and the answer is genuinely unknown and genuinely coming. And that is a rare and precious place to stand. Most of the science you learn about is finished, handed to you as a settled fact, the drama already over before you arrived. This one is live. The astronomers who found this atmosphere are, even now, planning the next observations, waiting for the next time this object crosses a suitable star, preparing to measure whether the gas has thinned or held. Somewhere, the data that will answer this is sitting in the future, waiting to be collected. And whichever way it goes, we win, because both answers are extraordinary. If the atmosphere is fading, we caught a dying breath and confirmed how fragile and fleeting these events can be. If the atmosphere is steady, we have found a tiny living world where we were certain none could exist, and we have to go back and ask how many others are out there doing the same. There is no boring outcome. There is no version of this where we learn nothing. We simply have to keep watching and let the cold, dark world tell us, in its own slow time, what it is. And while we wait, the discovery has already done something to the rest of the sky. It has changed how we have to look at everything out there. Part 9. The Graveyard That Is Not. Let me pull the camera back now, away from this one little world, and show you why this discovery is so much larger than a single object that almost nobody had heard of. Because the real weight of it is not really about 2002-1593 at all. It is about everything that surrounds it. Remember where we are. We're in the Kuiper Belt, that ring of frozen leftovers stretching out beyond Neptune, and the Kuiper Belt is not a handful of objects. It is a crowd. Astronomers estimate that there are tens of thousands, very likely hundreds of thousands, of objects out there larger than about 100 kilometers across, and an enormous number of smaller ones beyond counting, perhaps reaching into the trillions if you include every icy fragment and frozen comet. It is one of the most populous regions in the entire solar system, and for all of human history we have looked at that immense crowd of worlds and called it a graveyard, frozen, dead, unchanging, the most boring real estate in the sun's domain. Now hold that word graveyard up against what we have just learned. We called this region a frozen graveyard, a place where dead things lie still. But graveyards do not breathe, and one of the residents of this graveyard, chosen more or less at random, an utterly ordinary small object that nobody had any special reason to single out, turned out to have an atmosphere. So here is the question that should make the back of your neck prickle. If the first small, anonymous, supposedly dead Kuiper Belt object we examined this closely turned out to be wrapped in an impossible atmosphere. What does that say about all the others? Was this one special, a freak, a single unlikely exception in a population of genuinely dead worlds? Or did we just happen to catch the first example of something that is actually common, something that has been happening all over the Kuiper Belt this whole time, on countless worlds, while we stared right past it because we had already decided there was nothing to see? We do not know the answer to that yet, and I want to be careful not to overclaim, because honesty is the whole point of a channel like this. It is entirely possible that 2002-1593 is unusual, that it happened to be struck recently, or happens to have some quirk that makes it active, and that most of its neighbours really are the dead rocks we always assumed. One example does not prove a population, but one example does something almost as important. It proves that the thing is possible at all. Before this, the idea that a small Kuiper Belt object could have an atmosphere was not even on the table. It was ruled out by the rules. Now it has happened, in front of us, with the evidence recorded from 4 telescopes, and once a thing is known to be possible, you cannot unknow it. Every other small object out there has just become a question mark where before it was a closed case. The graveyard has not necessarily come alive, but we can no longer assume that it is dead. We have to go and check, and checking changes everything about how we treat this whole region of the sky. There is a phrase I keep coming back to as I think about this, and it is this: dead is a word we use for things we have not looked at closely enough. For decades these objects were called dead, but that word was never really a description of the objects. It was a description of our attention. We had not looked closely, so we filled in the blank with the simplest assumption that nothing was happening, and the moment we did look closely at just one of them, the assumption shattered. This is a pattern that runs through the whole history of astronomy, and it is worth noticing because it is humbling in the best way. Again and again, we have looked at some part of the universe, decided it was empty or quiet or finished, and then built a better instrument or pointed an old one in a new way, and discovered that it was busy and loud and unfinished all along. The emptiness was never out there. The emptiness was in our looking, and every time we forget that, the universe finds a gentle way to remind us, sometimes with a flicker of starlight on a winter night. To feel the scale of what this opens up, it helps to compare our little world directly with Pluto, the one object out here we know reasonably well, because the comparison is what makes the new discovery so unsettling in the best way. Pluto has an atmosphere, but Pluto earns it. Pluto is large, the largest object in this whole region, more than 2,000 kilometers across, and that size gives it enough gravity to hold a thin atmosphere, at least while it is near the closer part of its orbit. Pluto also has the right ices on its surface, nitrogen and methane and carbon monoxide, the volatile ones that turn to gas. So when Pluto has an atmosphere, it makes sense. It fits the rules. Pluto was never a problem. Pluto was the one allowed exception, the world big enough and well stocked enough to do what the others could not. 2002-1593 breaks that comfortable picture precisely because it is everything Pluto is not. It is a fifth of Pluto's width, far too small to hold gas by the old reasoning. It is, as far as we can tell, missing the volatile ices that supply Pluto's sky. It should be the deadest of the dead, a perfect example of the boring frozen rock the textbooks promised. And it has an atmosphere anyway. That is the whole shock in a sentence. The world that should most clearly obey the rule is the one that broke it, and because it is so ordinary, so representative of the vast population of small Plutinos and Kuiper Belt objects, its breaking of the rule cannot easily be set aside as a special case. If the most ordinary kind of object can do this, then ordinariness is no longer a guarantee of deadness. That is why the population question matters so enormously. There are not a few of these small objects. There are hundreds of thousands of bodies out there larger than about 100 kilometers, and uncountable smaller ones. We have now examined exactly one of them this closely, with the right technique, at the right moment, and it turned out to have an impossible atmosphere. 1 out of 1. We have no idea yet whether that ratio holds, whether the next one we check will also surprise us or whether this one is a fluke. But the mere fact that the first careful look revealed something nobody thought possible should make us deeply curious about the second look, and the third, and the 100th. The outer solar system has just become, in a single night, one of the most interesting places to point our telescopes, precisely because we spent so long believing it was one of the least. So the discovery of this atmosphere is not really the end of a story about one object. It is the opening of a question about thousands of them. It tells us that the outer solar system, far from being a static frozen archive, may be a place of slow hidden activity, of worlds quietly venting gas, of collisions and brief atmospheres flaring and fading, of processes we have not begun to catalogue because we were not looking for them. It tells us that the most boring region of the solar system may have been boring only in our imagination, and it raises the genuinely thrilling possibility that the next small world we examine this carefully, and the one after that, might have their own surprises waiting, their own impossible things, their own quiet contradictions sitting in the data, waiting for someone patient enough to notice. The graveyard, it turns out, was never a graveyard. We just had not heard it breathing, and the most remarkable part of how we finally heard it is who was holding the telescopes. Part 10. The Amateurs at the Frontier. There is a detail in this story that is easy to skip past, but I do not want to, because it changes who you imagine when you think about how a discovery like this gets made. When you picture the frontier of space science, you probably picture something enormous and expensive. A billion-dollar spacecraft launched on a roaring rocket, a space telescope the size of a tennis court, folded up and flung 1,000,000 miles from Earth, a control room full of engineers in matching shirts, applauding as a signal comes back from the edge of the solar system. And those things are real, and they are magnificent, and they have taught us an extraordinary amount. But that is not how this atmosphere was found. This atmosphere around a world beyond Neptune, the first new atmosphere discovered out there since Pluto, was not found by a spacecraft. No probe went there. Nothing flew past it. It was found from the ground on Earth by a team that included not only professional astronomers, but amateur ones, people with modest telescopes, the kind of equipment a dedicated enthusiast might set up in a backyard or haul to a dark field on a clear night. Let me be specific, because the specifics are wonderful. Yes, the team used a professional instrument, the 1.05-meter telescope at the Kiso Observatory, run by the University of Tokyo. That is a real research telescope. But alongside it, the observations that caught this atmosphere came from amateur-grade telescopes, instruments with main lenses or mirrors around 200 and 250 millimeters across, which is to say roughly 8 and 10 inches. Those are sizes that an amateur astronomer can own. They are sizes you can buy. What made them powerful enough to contribute to a frontier discovery was not raw size, but coordination and timing and modern cameras. Fitted with sensitive electronic detectors and pointed at exactly the right star at exactly the right moment, these everyday telescopes recorded the gentle fading of starlight that betrayed a layer of gas around a world billions of miles away. The frontier of the outer solar system, it turns out, is not always reached by spacecraft. Sometimes it is reached by a network of patient people on a cold night, all looking at the same faint star, knowing that for a few seconds something will pass in front of it, and that those few seconds might contain something nobody has ever seen. I find that genuinely moving, and I think it should change the picture in your mind of who gets to make discoveries. The objects out here are so numerous, and the events so brief and so scattered across the sky and across the surface of the Earth, that no single great observatory could possibly catch them all. There are simply not enough giant telescopes, and they cannot be everywhere at once. But an occultation traces a narrow path across the Earth, and if you can place enough observers along that path, even small ones, you can catch the event and measure it. That is a task suited to a community, to professionals and amateurs working together, spread across a country or a continent, each one holding a small piece of the sky. The discovery of this atmosphere was, in a real sense, a collective act, made possible because the frontier of the outer solar system happens to be visible, in fleeting moments, from the ground that ordinary people stand on. The edge of the map is not as far out of reach as it sometimes feels. On the right night, with the right preparation, it passes overhead, and anyone properly equipped and properly placed can be the one who happens to be watching. Now let me take you somewhere, while we are thinking about this little world that ordinary telescopes caught. I want you to leave the observatory behind, and the Earth behind, and stand on the surface of 2002-1593 itself, just for a few minutes, in your imagination. Picture your feet on the ground. The ground is not soil, and it is not loose rock. It is ice, water ice frozen so hard and so cold that it is as solid as bedrock, a dark grey plain stretching out around you, dim and dusty looking, tinted by whatever ancient material has settled onto it over the eons. The plain is not bright, It does not gleam. It is the grey of old ice in deep shadow, and it is still, utterly still, with a stillness you have never experienced anywhere on Earth, because there is no wind to move anything, no sound to fill the silence, no warmth to stir the smallest current of air. Look up. The sky above you is black, perfectly black, scattered with stars that do not twinkle at all, but burn steady and sharp because there is almost no atmosphere here to make them shimmer. And there, among the stars, is the sun. Not the sun you know, not a disk, not a source of warmth, not something you have to look away from. Here, the sun is a single point of brilliant light, intensely bright but tiny, no wider to your eye than a distant headlight on a far highway. It throws a thin, pale light across the grey ice, enough to cast your shadow, sharp and black, stretching away beside you. But you feel nothing from it. No heat reaches your skin. If you held out your hand toward that point of light, your palm would stay as cold as the ice beneath your feet. The sun out here is just the brightest star in the sky, and it rules over a world it can no longer warm. The role of amateur astronomers in this work is not a charming footnote. It is increasingly essential, and the reason comes straight from the nature of the events themselves. An occultation is visible only from a narrow strip on the Earth, and which strip depends on exactly where the object and the star line up. A geometry that shifts from event to event and falls wherever it falls, over land or sea, over cities or empty countryside. The great professional observatories are few, and they are fixed in place on certain mountaintops. They cannot move to catch a shadow that happens to fall across a different part of the world on a given night. But amateurs are everywhere, and their telescopes are portable, and there are far more of them than there are giant observatories. A coordinated network of dedicated enthusiasts can place observers all along the predicted path of a shadow, blanketing it, ensuring that wherever the event is visible, someone is there to record it. This is a genuine partnership, and it has become one of the quiet engines of outer solar system science. Professionals predict the events and refine the paths and provide some of the larger instruments. Amateurs contribute their numbers, their geographic spread, their portability, and increasingly their excellent modern cameras, which can record the rapid, subtle dimming of a faint star with real precision. Together they catch events that neither could catch alone. The discovery of this atmosphere is a monument to that collaboration, a frontier result made possible because ordinary people with modest equipment were willing to stand out in the cold and point at a faint star at a precise second, trusting that the few seconds they recorded might matter. And they did matter. They mattered enormously. I think there is something quietly profound in that, something worth carrying with you. The edge of the known solar system, the place we have been calling the frontier all night, is not sealed off behind billion-dollar barriers, reachable only by spacecraft and space telescopes. Part of it, on the right night, passes directly overhead, visible from your own patch of ground if you're equipped and prepared and lucky. The shadow of a world beyond Neptune can fall across an ordinary field, and an ordinary telescope can catch it, and in catching it can help rewrite a rule of planetary science. The frontier comes to us sometimes, sweeping silently across the turning Earth, and anyone watching the right star at the right moment can be the one who happens to see it move. And now the strangest part. All around you, invisible, is the thing that brought us here, the atmosphere. You cannot see it. It is so thin that it is, for all practical purposes, a vacuum with the faintest memory of gas in it. You cannot feel it. It would not stir a hair, would not press against your skin, would not carry the smallest sound. If you somehow tossed a handful of dust into the air, it would not drift and settle the way dust does on Earth. It would fly in a clean arc and fall, and yet it is there. A shell of gas, real, measured, wrapped around this little world, the very thing that by every rule we trusted should not exist. You would be standing inside an impossible atmosphere, on a dead world that is not as dead as we thought, under a sun that has become a star, in a silence older than the Earth itself. That is what this discovery actually means, translated out of numbers and into a place you could, in principle, stand. A faint flicker of light, 18 seconds of a star going dark, and on the other end of it, a real world with real ground and a real ghostly sky, waiting out there in the cold for us to understand it. And the reason it is worth understanding reaches back further than you might expect, all the way to the beginning of everything we know. Part 11. Time capsules with secrets. To feel the final layer of why this matters, You have to understand what these objects actually are, in the largest sense, and it is something close to miraculous. The Kuiper Belt is not just a collection of cold rocks, it is an archive. When the solar system formed, 4.5 billion years ago, it formed out of a great disk of gas and dust swirling around the young sun, and the planets grew by gathering that material together, sweeping it up, heating it, churning it, melting and remaking it again and again. The earth beneath your feet has been processed almost beyond recognition. It has been melted, mixed, folded, erupted, weathered, and recycled so many times over so many billions of years that almost nothing of the original material survives in its original form. The same is true of the other large worlds. They are remade things. They have forgotten their own beginnings. But out in the Kuiper Belt, far from the sun, in the deep cold, the leftover material was never gathered into a planet, never melted, never churned. It was simply left there, frozen, in the dark, undisturbed, which means that these objects are, in a very real sense, time capsules. They are samples of the original material the solar system was built from, preserved at the temperature of deep space, essentially unchanged since the planets were young. When you look at 2002-1593, you're not just looking at a small cold world. You're looking at a piece of the past, a frozen fragment of the same primordial material that became the Earth and the oceans, and eventually you. The ice is on its surface, the chemistry locked into it, the very fact of its existence, all of it carries information about conditions in the early solar system that has been erased everywhere closer to the sun. These objects are how we read the first chapter of our own story, the chapter that the planets themselves have long since overwritten. They are the only copies left of the original text. And now think about what an atmosphere adds to that. We thought these time capsules were sealed, inert, finished, that their only value was as frozen snapshots of the past. But if even one of them is active, venting gas, changing, doing something, then they are not just snapshots. They are still being written. They have a present, not only a past. The discovery of this atmosphere adds a chapter to the archive that we did not know was there, a chapter about what these worlds are still doing, billions of years after we assumed they had gone quiet. It tells us that the early material of the solar system, preserved out there in the cold, has not finished surprising us, that there are processes still running in objects we filed away as complete. Every assumption we make about how worlds form, how long they stay active, what keeps them warm, how atmospheres come and go, all of it now has a new and unexpected data point, a small grey world that refused to be as simple as we needed it to be. Let me sit with the largest version of this thought, because it is the emotional centre of the whole story for me, and I think it lands harder the longer you look at it. For decades we called this entire region dead. We called these worlds boring. We filed them away, all of them, hundreds of thousands of worlds, under a single dismissive heading, nothing to see here, and we turned our attention to flashier things. And we were wrong. Not wrong about the physics was reasonable. We were wrong in a quieter and more human way. We had decided that something was finished before we had really looked, and the universe, patient as always, waited until we finally looked closely at just one of them, and then it showed us, with the gentlest possible signal, a star fading instead of blinking, that dead was never a property of these worlds at all. Dead was a property of our attention. The word said more about us than about them. Consider what it means that almost nothing of the original solar system survives in its first form. The Earth has been melted and remade so thoroughly that the rock beneath your feet bears almost no resemblance to the primordial material the planet was built from. Mountains have risen and worn away many times over. Oceans have come and gone. The very continents have drifted and collided and split apart again. The whole surface has been recycled again and again, erasing the record of the beginning. If you wanted to find a sample of the actual material the solar system formed from, untouched, unmelted, unchanged, you would not find it here. You would not find it on any of the large worlds, all of which have been processed by heat and time. You would have to go somewhere that nothing ever happened, somewhere so cold and so far that the original material was simply left in place and forgotten. That somewhere is the Kuiper Belt. These objects are the leftovers that were never gathered into a planet, never heated, never remade. They have been sitting in the deep freeze of the outer solar system since the very beginning, holding their original chemistry, their original ices, their original structure, essentially intact across 4.5 billion years. When we study them, We are studying the raw material of creation, the stuff that the planets, including our own, were assembled from. They are the only unedited copy of the solar system's first chapter, the one record that was never overwritten. That is why even a small anonymous object like 2002-1593 is scientifically precious, far beyond its size. It carries information that exists nowhere else, the memory of conditions that the rest of the solar system has long since forgotten. And so to discover that one of these archives is not inert, that it is still doing something, still changing, still capable of wrapping itself in an atmosphere, is to discover that the archive is not closed. The first chapter of the solar system's story, we assumed, was finished, fixed, frozen in place for us to read at our leisure. But this little world suggests the story is still being written, even in its oldest pages, that processes we did not anticipate are still running in the very objects we treated as static relics. The past, it turns out, is not entirely past out there. It is still moving, still warm in places it should be cold, still surprising us with what it can do. The time capsule has a present tense, and that changes how we have to read everything it has to tell us about where we came from. There is a practical reason, beyond pure wonder, that scientists care so much about reading these original archives, and it comes down to a question we have barely begun to answer, which is how planets and worlds actually form. We have theories, good ones, about how a swirling disk of gas and dust around a young star gathers itself into planets, but the details are genuinely hard, and the outer solar system is one of the few places we can check those theories against preserved evidence. The sizes of the Kuiper Belt objects, their compositions, their orbits, the way they are distributed through space, all of it carries clues about what the early solar system was like and how it settled into the arrangement we see today. Each well-studied object is a data point against which the theories can be tested, and an object that does something unexpected, like wearing an impossible atmosphere, is an especially valuable data point because it reveals a process the theories did not predict, a gap between what we thought happened and what actually did. So the atmosphere on 2002-1593 is not just a curiosity, it is a thread that, pulled carefully, could lead back to a better understanding of how all worlds, including our own, came to be. If small bodies out here can stay active far longer than we believed, or can be reshaped by collisions in ways we underestimated, then our models of how the solar system formed and evolved need adjusting. The story of one tiny world holding an impossible breath connects, through the long chain of cause and consequence, to the largest question of all, the question of where everything came from, where the Earth came from, where the material that became oceans and air and living things first took shape. That is the strange power of these distant, frozen, anonymous objects. They look like nothing. They are in truth among the most important witnesses we have to our own beginning. How much else, then, have we filed away too soon? How many other regions of the universe have we glanced at, found unremarkable and set aside simply because we had not yet built the instrument or pointed it the right way, or waited long enough for the one fleeting moment when the truth would show itself? This is the real gift of a discovery like this one, beyond the specific facts about a specific object. It is a reminder, delivered quietly from beyond Neptune, that the universe is almost never as finished as we assume, that the boring label is usually a confession of how little we have looked, and that the next impossible thing is probably already sitting in some dataset, or waiting in some patch of sky, perfectly ordinary on the surface, perfectly extraordinary underneath, biding its time until someone pays attention. There is something humbling in that, and something hopeful too, because it means the age of discovery is not behind us. It means the sky is still full of secrets, even in the places we were most certain held none. And it means that the next person to find one might be looking through a very small telescope on a very cold night, watching a very faint star waiting for it to fade. Part 12. Holding its breath. So let us come back, at the end, to where we began, all the way out at the edge of the map past the planets, past Neptune, in the cold and the dark of the frozen graveyard that we now know is not a graveyard at all. And let us look one more time at this small grey world, 2002-1593, an object so ordinary that it does not even have a proper name, only a string of numbers, an object that for the entire history of astronomy was exactly the kind of thing nobody bothered to study. It is still out there right now, as you listen to this, drifting along its slow orbit, taking centuries to circle the distant sun, exactly as it has for 4.5 billion years. Nothing about it looks special. Nothing about it ever did. And yet it is wrapped in a thin shell of gas that should not be there. An atmosphere too small to keep, too cold to make, built from ingredients it does not seem to have, and we do not know how. We do not know whether that atmosphere is the breath of a living world, vented patiently from some warm hidden interior that has no business still being warm. We do not know whether it is the last exhalation of a brief and dying event, the smoke clearing after a recent collision, fading away even now, destined to be gone within 1,000 years, caught by us in the single fleeting moment it existed. We do not know what the gas is made of. We do not know how long it has been there, or how long it will last. We know almost nothing about it, except the one thing that matters most, the one thing that overturned a rule we were sure of. We know that it is there, and we know that the way we found out was the gentlest signal imaginable. The star did not blink, it faded. I keep returning to that because I think it is the truest image in this whole story, and it means more the longer you hold it. We expected a blink, a clean yes or no, a sharp edge, the universe giving us a simple answer. Instead we got a fade, a soft dissolve, an answer with blurred edges that turned out to contain far more than a clean blink ever could have. And that, I think, is how discovery almost always actually works. We go out expecting the universe to confirm what we already believe, to give us the sharp, clean blink of a settled rule, and instead it gives us something softer and stranger, a gradual fading at the edges of what we know, a place where our certainty thins out and bends like starlight through gas, and on the far side of that fading there is something we never expected waiting in the dark. The frozen graveyard taught us that. A single faint star, dimming slowly on a winter night, taught us that the rules we were most confident about had a soft edge we had never noticed. I think the reason a discovery like this stays with you, long after the specific numbers have faded, is that it is not really about a single object at all, it is about a way of seeing. We are creatures who like our categories settled, who find comfort in deciding that this region is empty, and that question is answered and this kind of world is dead, so that we can stop wondering about it and turn our attention elsewhere. And the universe, gently, patiently, keeps showing us that our settled categories are provisional, that the line between dead and alive, between empty and full, between known and unknown, is almost always drawn too early and in the wrong place. The frozen graveyard beyond Neptune was a category we drew, a box we put thousands of worlds into so we would not have to think about them, and a single faint star, fading slowly on a winter night, reached into that box and showed us it was never as closed as we believed. And so the little world goes on, out there in the cold, holding its breath. That is the image I want to leave you with, because it is not really a description of physics anymore, it is something closer to a posture, the posture of the whole outer solar system as we now have to see it. A tiny grey world, wrapped in an impossible atmosphere, turning slowly in the dark, holding a single thin breath that it should not be able to hold, quietly daring us to come closer and find out how. It is not asking to be feared. There is nothing terrifying out there in the way a monster is terrifying. What is terrifying, if anything is gentler than that, and larger. It is the realization of how much we do not know, sitting right next door in our own solar system, in a place we had already decided was empty. It is the recognition that dead was only ever a word for things we had not looked at closely enough, and that the universe is patient, and that it will keep holding its breath, keep keeping its secrets, until we are ready to pay attention. For 4.5 billion years this world waited, silent, for someone to notice. And on one cold night, when a star faded instead of blinking, we finally did. The question now is how many others are out there, all across that frozen dark, each one holding its own quiet breath, waiting for us to look. We have only just begun to find out, and somewhere beyond Neptune, in the cold and the silence, a tiny impossible world is still waiting, still holding on, still daring us to understand,